Good evening, everyone. We'll pick up where we left last time. So the plan for today is to wrap up BLE and then going to kind of look at some of the options, some of the other wireless technologies relevant to IoT. We'll kind of at a less detailed level, we'll examine some of those. So last time, if you recall, I described that how in that Bluetooth LE kind of rides on the initial handshake that classical Bluetooth used to do in terms of advertising and pairing with a device. So basically, BLE just rides on top of it. It was a separate um, uh, technology which was kind of strapped on top of classic Bluetooth LE. And so if you recall, we had kind of this two notions, uh, central and peripheral. So central is the client and peripheral is a server. So a sensor, for example, or providing the data. And there are two distinct phases, one where the peripherals advertise themselves and one or more devices, one or more central devices may listen to it. So this in itself is quite useful. And so you can have tiny little sensors advertising information just carried on the advertisement packets. And then subsequently, you also have a notion of a central device requesting additional information. And that's the only way bidirectional information goes through. So if you see carefully at this picture, during the advertisement phase, the information is just one way. But it's only when there is a direct one-to-one interaction between central device and a peripheral that the bidirectional aspect is possible. Okay, so what we'll do is to examine what happens, like how this information goes back and forth. So we had looked at the slides. I'm going to skip through these. Okay, so I'm just skipping through. Okay, so key concept in Bluetooth generally and specifically for relevance to BLE is this notion of generic attribute profile. So Bluetooth, like many other standards like USB and all, is defined in terms of a whole bunch of profiles. So profiles are basically sort of information level protocols on top of the underlying physical layer. So generic attribute profile is something that already existed in Bluetooth, and BLE makes use of it. So what it does is it lets two devices exchange information in a systematic manner. So in case of GATT, there are two related concepts. One is called services and one is called characteristics. And this comes into relevance only when you have a connection established between the two devices. So it's not relevant during the advertisement phase. During the advertisement phase, all we had were those 31 bytes, and there is some of those bytes were left open for manufacturers use, and that is how Apple and subsequently Google and others began to sort of write information on top. So what happens in this particular in case of GATT is that there is almost like a set of registers that the device exposes, and some of them are read only and some of them are write only. And it basically allows for information to be exchanged in terms of those. So we're going to dive into it in a couple of slides. What happens is that using a connection interval, the central, your phone, computer, whatnot, is going to connect to the peripheral that it had discovered and set up a connection with. And at that point in time, this communication takes place. So at that, once the connection goes into play, you basically have a server-client relationship at that point. So the phone seeks service from the peripherals, and it's the peripheral where the information is kind of like a data structure, or that is being stored. So what the client, in this case the central, does is it sends requests to the server. So all these connections are initiated by the client, and there is a particular interval attached to them. So essentially what's happening is that every so often, every connection interval which was negotiated at the time of connection, the master, your phone, is going to connect to the server, the peripheral, who will respond to this information. So the request that goes out will consist of some sort of a query. So so this is where sort of GATT comes into play. So GATT profile describes this concept of service and characteristics. One way of thinking about them is they are kind of like classes or objects corresponding to some classes. So service corresponds to different classes of information, and characteristics are fields within that service. So for example, you may have a profile corresponding to heart rate sensors, for example. So there's a heart rate profile. So a lot of these profiles are standardized, and within that you have services. There is some services which are mandatory, and some are optional. So and each one of them is given a unique ID. So you can basically just think of it as way of hierarchically organizing the data. So in this particular case, there is a heart rate service. It has an ID, and then it consists of a bunch of characteristics. There is a heart rate measurement. There's a body sensor location. There's a heart rate control point. So there could be a whole bunch of such things. And some of these characteristics are readable, read-only, and some of them are writable. So for example, using this, your phone can connect to the sensor and get the latest reading, for example. Or using the writable one, it can go and configure, let's say, for example, some parameter of the sensor. So there are a whole bunch of such standard services, and this is how apps and sensors can talk to each other in a standardized manner. But there's a lot of custom stuff that you can do. You can always define your own profile, your own service, your own set of characteristics under these. So there's a bunch of standard things, and then a whole lot of characterization, a whole lot of customization that is possible. So in this particular heart rate example, there is a heart rate measurement characteristic. It has a standard UUID. Those of you who don't know, UUID is like a global naming convention that has emerged. So these are basically just some long string of numbers. And in this particular case, this particular characteristic describes what is the type of the data. So oftentimes you may have sensors which are notionally measuring the same thing, but they may be using different units. And also in this particular case, it's saying whether the format of the data is an 8-bit unsigned integer or a 16-bit unsigned integer. There are other kind of services. There is another service which is provided as a UART service, and kind of the idea is on top of BLE, you basically mimic a serial port connection, send characters at a time. So that's another example. And there are a whole bunch of these things. So there are a whole bunch of services supported, and each one of them would have some readable characteristics and some writable characteristics. And usually Bluetooth chips already provide support for it, in the sense that the low-level hardware usually will have a protocol stack associated with it, which will give this abstraction. So even from the level of your software, you will basically update a characteristic. You'll tell the Bluetooth stack, this is the new value of a particular characteristic, and it deals with it. So, if you look at the APIs and all that are available, they basically talk in terms of these. So you have service, characteristics, and within the characteristics, you have a bunch of different types of information. What's the type, what's the value, and some associated properties. So that's how the information gets organized. Then another aspect is what goes over the air. So Bluetooth, as I mentioned last time, relies on what is called as frequency hopping. So what's happening is, so you have a bunch of channels, and you can think of each channel corresponds to a different hopping pattern. And the reason we hop is because certain frequencies in a given space may be noisy because of presence of microwave ovens and things like that. During one slot, while sort of, so when two parties tune to the same channel, essentially they have tuned to the same hopping pattern. So they are synchronously hopping across frequencies. So you have, again, a bunch of frequencies. Channel is a hopping pattern, and over time, while you are in a particular channel, you are going to hop according to a particular sequence. So and there is a whole sort of, in the main Bluetooth, there is this whole process defined that how do you synchronize with someone, because if the other party is hopping and you know the hopping pattern, but you don't know where within the cyclic hopping pattern the other party is, then you have to wait there for a while until you synchronize. So all of those details are handled by the standard Bluetooth. But once you are at the same in the same channel at the same frequency now, then you send a frame, a link layer frame. And in case of Bluetooth, it looks like what is shown out here. So there is a preamble. Anyone knows why we send preambles in packets, in frames in communication? We had discussed that a couple of slide sets ago. So what's the purpose of preamble when we send bundles of information over a communication link?
Isn't it basically to like synchronize communications in some sort of way?
Yeah, it is about synchronization, but what do we synchronize? So remember when we were talking about time sync, I had said that there are various kinds of synchronization. One of the problems in communication is that your two parties don't have the same common clock source, right? So while we may have that, we are both talking at, let's say, 1 mega symbols per second, but maybe mine is a little bit different than precisely 1 mega symbols per second. So if I were to sample your incoming signal, I won't be able to do it. In normal hardware, we don't face this problem because you have a global clock controlling all the chips on your board or all the logic in your chip, for example, right? But over a network, that's not possible. There's no global clock that both parties have access to. So we roughly know coming in that what your clock would be. That's part of the standard. But then we have to fine tune it, right? And I had talked about that phasor measurement unit, which kind of says, which basically tells me my local clock, how much different it is from the incoming clock. Now, what preamble is a known pattern. So the idea is I know what I'm supposed to receive, and I'm going to tweak my clock until I make sure that I receive that correctly. So preamble is serving start of the packet as well as letting me tweak my clock so that I am in sync with whatever the clock of the sender was. And then once I have tuned my clock frequency, then I can sample the remaining symbols correctly. So what it also means is, depending upon my clock drift and all, I can only that tuning will remain valid only for some period of time, because after the preamble, I don't know rest of the content. So I have no longer any ability to further synchronize. Okay, so basically that's why you have a limit on how long a packet could be. It will depend upon how good your clock is and how good you were able to synchronize the frequency out here. Okay, so there is a preamble which is serving all these purposes, and of course, it's totally wasted time, right? It's taking up bandwidth, it's taking up energy, and of course, it's taking time. But we need it. Then you have the address, in this case, a 4-byte address, and then followed by what they call as the PDC, which is the payload part, and then finally the CRC. And within this, there is kind of a whole bunch of, there is advertisement channel type data unit, what they call as PDU, protocol data unit, or a data channel type. And within that, you have kind of further some substructure that there is a header corresponding to this PDU, and there is a payload. And likewise out here, there is a header, payload, and then again some sort of additional information. And all of these things are structured. So, and this is defined by kind of, again, the underlying main Bluetooth protocol. Okay, so shortest packet 80 bits within 80 microsecond, longest packet 376 bits in 0.3 millisecond. Within for our purposes, remember what I said was that BLE makes use of the advertisement channel, right? That is where the initial information goes out. So within the advertisement channel, after you factor all the redundant information, you're left with 31 bytes. And the idea is that this 31 byte of information could be used for your own custom purposes. And this is what, starting with iBeacon and later on other similar products, they kind of harness that. So basically, when you are advertising, when a peripheral device is advertising, it can send 31 bytes of information. Later on, when you are connected and all, then this data channel PDU comes into play, okay? And there, the information structure is different. So that's what goes over the air. So for, so as you can see, there is basically the main Bluetooth, and then there is this BLE, which is layered on top of it, intended to be something where you don't need any pairing. You can even send out information just as part of the advertisement. So BLE, in a way, you can say it's kind of an extension to the original Bluetooth. And the idea was that this allows for very low energy devices, sensors, which are just at a low rate, which are going to transmit things and all. And yet at the same time, we are able to kind of reharness the hardware and the underlying protocol infrastructure that Bluetooth had already put in place. So Bluetooth had come many years earlier, and BLE came much later. So essentially what it means is that you basically have two types of devices which only support the original Bluetooth, which is Bluetooth BR EDR, and devices that support Bluetooth LE. So a single mode device is one which only supports BLE, and a legacy device is one which only supports BR EDR, and a dual mode device is which supports both. So you will often find things, particularly low-end sensors and all, which only support BLE. They don't have the capability of doing the full-blown extended data rate version of Bluetooth. So that's what you see out here. There is the classic Bluetooth, BR EDR. There is a dual mode Bluetooth, which supports both that and BLE. And then there are BLE only devices. And then within BLE, you will see some devices can only be peripherals, and some devices provide support for both being a peripheral and being a client. Now, your devices like your phone usually can be both peripherals as well as centrals. Many of the little embedded devices you'll find can only be the peripherals. That is, they can only serve the data. But with the emergence of Bluetooth 5, where we also have Bluetooth meshes, there the devices are expected to play both the role, right? I mean, at some point in time, you are sending information, another point in time, you are requesting information. So the newer BLE 5 compliant things basically typically can do both, including the chip on the little boards that we have. So you can operate them so that much like your phone, sometimes they can be central, sometimes they can be clients. Now, what often happens is that the software, not all BLE software stacks support everything. So that's a separate problem. But for example, Arduino's BLE stack is a little bit primitive. On the other hand, the NRF, the chip manufacturer, they give their own stack, which is pretty rich and supports all sort of features. So Bluetooth 5 is the more recent thing, and it besides mesh, it introduced a whole bunch of other things also, including faster and longer range modes. So basically, as this table kind of shows, originally in Bluetooth 4, we only had what is there in the first column out here. So LE1M, which was 1 mega symbol per second with a data rate of 1 megabit per second. So we are basically sending 1 bit per symbol. And this is kind of like something that every device has to support. But then Bluetooth 5 introduced 3 other modes. One where we have same symbol rate, but we are carrying fewer bit per symbol, essentially by using a different modulation standard, so that our data rate is lower, but that results in a more robust link, so you can go longer distance. So the idea is that this mode is used when you need to communicate over a longer distance. This is optional. Then you have another one, which is an even lower rate. In this particular case, even fewer bits per symbol. And the reason is because some of the remaining stuff is going into FEC, which stands for forward error correction. But the idea is here, again, we can get an even more of a range multiplication. And then finally, they go in the reverse direction, which is they have a mode where the symbol rate is higher. So we are sending 2 mega symbol per second, and therefore 2 megabit per second, no error correction, and you have a shorter range. So essentially, kind of mandatory mode is what originally existed, but now you have kind of a slower versions which are longer range or more robust, and faster version which are shorter range. So there's a lot of at 2 megabit per second, you might imagine you can even over BLE you can begin to send audio and some meaningful sensor data. People even do imagery. I mean, 2 megabit per second if you can. So if you have 2 megabit per second, that means by the time you take all overhead and all into account, you're probably sitting at a few tenths of kilobit per second. Sorry, a few hundred kilobit per second. But that is sufficient to do a lot of stuff like sending imagery also and things like that. So there are products which are kind of making use of these. This is some data I have found on real life numbers that you can expect to get. So what you see out here is that the data throughput in the baseline was for 1 megabit per second, you were getting around 800 kilobit per second of like actual application level data throughput. With BLE5, you can, with the high rate mode, you can go to 1.4 megabit per second, and with long range mode, you are kind of in this. And remember, all of this is shared, so it also depends on how many other clients you have, and of course, this also depends on what the connection how frequently the exchanges are happening, because part of that reason, part of the thing in BLE is that you also duty cycle, right? So remember that advertisement interval that I had talked about, which can range from milliseconds to seconds. So all of these come into play in terms of the actual throughput that your data rate that your device will see. So obviously something like microphone sending acoustic data would probably have be sending stuff more frequently. But the nice thing out here is that you could with these things, even in that plain advertisement mode, you can do a lot. Now, of course, it's one way only. So it's there is no way for you to kind of go back and tell anything else to the device. It's one-way data transmission. You cannot send any data to the device. You can request one more additional packet, if you recall, but that was it. There is no way that you can send any semantically useful information to the device. For that, you have to establish the connection. So with this whole notion of beacons and sort of making use of the advertisement part of Bluetooth in these ways catching on, so there is a lot of other things that when Bluetooth 5 came into being that they added to it. So in particular, essentially advertisement mode of Bluetooth became pretty strong. Kind of the idea being that maybe larger amounts of data could be sent around. And some of it has to do with essentially that the older Bluetooth, as I had explained, for things like iOS devices and all, requires special chips and all, whereas BLE is kind of like the lingua franca at this point. So you see BLE being built in everything, your locks and smart switches and all sort of stuff. So in they kind of added additional features, mostly to allow richer forms of data being advertised, larger amounts of data being advertised, as well as making things more efficient. So you would see that my original stuff about that you can only send 30 words is no longer true. Bluetooth 5 compliant devices can send far more richer forms of information. So essentially for IoT devices, this whole BLE mode has become probably the most dominant form of communication, particularly in short range spaces, and because your phone support it, and so it has really caught on. Big business, and changes in Bluetooth 5, there is kind of even more richer information than the first generation devices. So you can imagine, and to some extent it already happens, right? I mean, there are apps that you can get for your phones where you can see what all beacons are nearby, you can query them and all, and as long as they are not using any crypto on top of it, this information is for free. Now, what happens is that obviously these sensors are also being used for a lot of sensitive stuff, right? I mean, there are medical sensors and things like that, and you probably don't want that data to be sent out in a mode where anyone can access it. So in in original Bluetooth, the pairing took care of it, right? You would pair a device so that it will only talk to you. So there's a counterpart of that out here also, which is information has to be, can be a particular sensor while it is making the BLE, may be cryptographically associated with a particular application. So like, for example, maybe your Fitbit will only give data to, will encrypt the data in a manner so that only the valid Fitbit app can read it. And so that's, or for example, yours can only talk to the valid app. So you don't want other apps to be doing this, because what happens is that information comes to the operating system, and then an apps can subscribe to it. Okay, so any app can get any BLE packet which is coming in, can listen to it. So it becomes the responsibility of the application to kind of then make sure that no one can pilfer that information away. So this BLE has also been a source of lots of security issues. When some of these things get broken, you can get sensitive information. Like, for example, let's say I come near you and on my phone I see that, oh, you have a particular kind of BLE device. I don't know, like, for example, let's say for blood sugar level, well, or insulin pump or things like that. Then I can immediately kind of make inferences about your medical condition, things like that. So there are, along with this advertisement, comes issues of privacy and security as well. Also, there have been some bugs in Bluetooth stacks which have led to issues where you can make use of the Bluetooth messaging to actually compromise the other devices. So I recall some news items a year or two ago, I think it was with Fitbit, you can spread malware through that. So there are these kind of issues as well. And I think it took a while for the protocol stacks to become good and robust. But there are still sort of considerable challenges. Not every protocol stack is sort of equally well designed. So some of the things that Bluetooth 5 added, larger packets so that you can advertise more stuff. You can chain advertisements, so send out a packet and then I can just repeat it, right? I mean, here you can split content across a bunch of advertisement packets, essentially creating pointers from one to another. So you can essentially send a list of advertisements which collectively give a larger amount of information. There is a concept of advertisement sets, which is essentially I can broadcast different pieces of information over the same device. And a bunch of other stuff about optimizing the duty cycle. So there's a lot of sort of under the hood stuff which is happening. I'm not going to describe these. I can skip these, I think. Let's see. Yeah. Okay. So much for BLE. So it's I think the main thing is it's basically as close to having a universally accepted wireless technology for IoT, at least in short range space that there is. So pretty useful and pretty easy to work with. So changing gears, this is not obviously the only wireless technology for IoT that exists. There is a whole rich space of stuff beyond BLE, and part of the reason simply is that BLE is targeted at a particular. There is a whole bunch of other stuff. So what I wanted to do was to give you a sense of some of that. So wireless beyond BLE. So BLE itself is basically designed, at least started out, it was designed for kind of what you would say is a cellular model of communication, which is we have these base station type things, or kind of the centrals, smartphones, but oftentimes it's not a smartphone. Sometimes these are also wired gateways to which devices talk. And it's a model which exists obviously in cellular thing, in your Wi-Fi and all, they all use. So a lot of wireless technologies are therefore like this, but also there are other models which wireless communication takes place, and just want to present that so that as you see some of the specific technologies, you will see what gets used. So the other very common form of communication is mesh networks. We have kind of I've referred to it along the way, but essentially it is this concept that I can have a bunch of devices talk to each other directly or through each other. So two things are relevant out here. So firstly, there is this notion of just two devices talking to each other directly through a point-to-point link. So there is this thing called like Wi-Fi Direct, for example, where my phone can talk to your phone using a direct link. One of the device operates as the server, the other or the base station or access point, and the other is clients. But more generally, you have this setting where you may have a whole bunch of devices in a network, and they're kind of forming this kind of a multi-hop network. So the idea is any device can send stuff to a farther away device through kind of a set of things. And this is a very common model in many products, particularly for home automation, building automation kind of things. And the reason being that they want to avoid this pain of kind of installing access points all over, so that every device is within one hop of access point. So kind of the idea is that you have a home gateway, and then you put these smart devices all over, and then as you install them, they discover the right network and then establish them. So all these smart switches and smart lights and these kind of things, they work in this principle. So all the homeowner has to do is to put a gateway at some point and the other devices kind of configure. So this is often called as self-configuring wireless. Okay, essentially when a device comes up, there is some sort of a search process goes on. They flood the network and then they discover who are their neighbors, and then they establish a path, a routing table which tells them what path to take to go to a different node. So there are many different ways of routing in this thing, but a very common one for small networks simply is that every device will have a little table telling them that if they want to go to another device, what route they should take. So like, for example, let's say I am talking about this device, this particular device, then maybe it will have a routing table. Let's say this device is A, and to reach B, maybe there are two possible paths, but maybe the routing table will say, if you want to go to B, go to C, and then C will say, have something which tells it that if you want to go to B, you should go to D, and so on and so forth. So at every node, there will be a routing table, and at every node, and that routing table, every time you add a new device or something, you'll have to update that. So there are sort of protocols defined for that purpose. It can, as long as you don't have mobility, this is not too bad a process, but it takes time. I mean, some of these products take a fair bit of time to discover and find their place in the network. The other challenge is that if these are devices that are also sleeping, so it could be that A wants to reach to B, but C is sleeping. So in the presence of sleeping devices, that duty cycle devices, this can be quite challenging. More technically, what we have are these topologies. The idea is that you may have a mix of devices in a given thing. That some of them are purely wireless, but others are wireless, but then on the other side they are so basically three kind of things: wireless, so wireless plus battery. Then you have wireless but powered, and then the other issue is wireless plus wired and powered. So these are the three kind of things that you will find typically, right? I mean, other combinations don't make any sense. I mean, it would be pointless for you to have wired network but battery operated. That typically is pretty uncommon. So these are the combinations. So your wireless plus battery operated are your most resource constrained things. Wireless but powered are still useful. So you avoid the pain of running an Ethernet cable to that point. You can put this stuff anywhere, but it is powered. There is technology which lets you communicate over power lines that also exist, but frankly, electronics for doing that kind of communication, essentially they create an Ethernet like communication over your AC wiring, never really took off. They were expensive. They ate a lot of power. I tried them in my home many years ago when these technologies were being talked about, but never really took off seriously. So it's a dead technology at this point. Essentially, Ethernet and wireless are really kind of your two options at homes, and all these funkier technologies of coax cable and electrical wiring really kind of died, or telephone wiring, they all died. Then wireless plus wired is what gets used for gateways. Of a lot of products now basically have that, or sometimes they may have wireless of two types and then powered. So like you may have a proprietary IoT specific wireless on one side, and you may have a Wi-Fi on the other side, and they are powered because these are gateways and they need to stay up for a long time. So maybe that's another option to consider, which is so maybe you can say there is local wireless plus I don't know how to describe them. So sometimes this may have two two alternative wireless links. Okay, one for local and one for wider. So this is essentially kind of the whole space and kind of the richer model that you see. Now, one thing that makes these different forms of wireless that you see different, part of it is kind of the layer issues, what power and all they are optimized for. But usually one of the biggest differences, how do they share the wireless link? And just wanted to describe that a little bit because that's probably the most critical part when it comes to wireless communication, how this part is handled. We saw a little bit of that when we talked about time sync and that how that helps with communication, the whole notion of medium access control protocol. But just wanted to describe that a little bit more in detail. So essentially, our challenge is that when radios send at the same time and the same frequency, then you have collisions that can result, and collisions mean that the packet is not received. So if A is trying to send to B, and C is trying to send to D, but if they are transmitting at the same time and they are in the same general area, then neither B nor D will get the packet. We did see one exception to that last time, which is if the communications, if the packets are identical and are being sent perfectly synchronized, then we can still send stuff. So MAC protocols really are designed to control when a node can transmit, and the idea is that we want to transmit such that there are no collisions. Now, there are other ways also you can ensure that packets don't collide. You can send them on a different frequency. You can send them far away, like two different rooms, for example, or you can send them using what is called as a different spreading code, okay, which you may have seen in your COM courses, but there are ways in which you can send stuff so that the collisions are not that material. Frequency hopping, which I mentioned for Bluetooth, is part of that. Two different channels may use different hopping patterns. So once in a while they may collide, but generally speaking, they will, the two channels will be on different frequencies at any given point in time. So when these wireless stuff are designed, there's a whole bunch of stuff, but for IoT stuff, things, the most dominating concern usually is energy efficiency. And then all the other stuff like we can scale. Part of the issue is that large number of devices, not be very bandwidth hungry. A lot of these parts of the spectrum which are given to these devices are relatively tiny, and as we are getting more and more devices, that becomes a problem. So there's a whole bunch of factors that help drive this thing. So at a very high level then, kind of in wireless historically, one notion has been that, I'm just going to fix certain frequencies and almost like create a permanent connection. And this is how a lot of the earlier wireless stuff operated. Like, for example, some of the security sensors at homes or wireless microphones and all. Okay, those were in this, but essentially this is very inefficient and not particularly kind of useful. The communication nowadays are all packet oriented, and within that, at the end of the day, at some point in time, you're going to have a channel of some form, which over time you are sharing among multiple devices. And very broadly, it's a problem of scheduling. Very similar to what we saw in the earlier part of the course, where our problem was which task gets to run on a CPU. It's the same problem out here, which is what node gets to transmit on a communication link. Okay, so it's essentially a scheduling problem. And like in computing, it's some similar thing. I can kind of time slot my resource, so I can do it by turn, but that requires synchronization. Or one of the very common thing out here is random access, that we let things transmit, and if we are lucky, they will not collide. But if they do collide, then I do some corrective action. There is no counterpart of that in computing. We can't have just say, oh, I'm giving the CPU to two tasks and let them both run and they will trash each other. There's no counterpart out here. But in communication, that does exist. So almost every significant wireless standard that currently exists essentially goes after this random access model in some form with some limited support for time-based scheduled access. That is, we actively try to give turns according to some manner. So to give you an example, Wi-Fi, which is used by a lot of IoT devices, even though it didn't emerge that way, and the reason it's not used in IoT that heavily is because it's power hungry. The not because of the MAC protocols, but because of the modulation schemes and all which are used. So it's not a low power optimized thing, but there have been attempts at low power Wi-Fi and all, but never to a level where they would beat things like BLE and all. So in Wi-Fi, basically you have the underlying channel, which is a shared physical channel. On top of it, they run a MAC protocol, which is based on that random access. If you have done ever very much the way Ethernet works, collision sends multiple access with collision avoidance. I'll describe that very briefly. But then on top of it, the Wi-Fi basically provides two kind of services. One is what they call as asynchronous services. You have a packet, go ahead, send. If there's a collision, you back off, try to resend. But then, because Wi-Fi also gets used for a lot of time-sensitive traffic, such as audio data or video data or things like that, they also have a time-bounded type service where you can reserve certain time on the channel, and then every so often your node will get to transmit. So you get kind of like a fixed bandwidth to some extent. It's still possible that someone may trash you something else running because there may be other Wi-Fi networks in the same neighborhood, but it tries to give you a guaranteed access of some form. So let's see how it kind of works out. So of 802.11, and it's very similar in many other Wi-Fi, many other wireless networks is the following. There's a source, there is a and then there are other entities. The source needs to transmit a packet. So what the source does, it listens to the wireless channel for a small period of time. So DIFS is a parameter which is defined by the standard. It's a very tiny fixed interval of time. So the idea is, I want to transmit on the channel. I'm going to hear for a little bit to make sure no one else is transmitting. And then I'm going to transmit the data. And then after having done that, what I'll do is wait for a certain period of time. Okay. Now, meanwhile, other parties, there may be someone else who also wishes to transmit the data. So there are two possibilities. One is that this other party, by the time they try to transmit, so that they didn't decide to transmit exactly at the same time. So in theory, it's possible both the nodes started checking for their DIFS at exactly the same time. But in general, barring that situation, what will happen is, let's say this other party kind of woke up somewhere at a later point in time, and it will wait for a DIFS time, and then it will see sources transmission, and then decide to wait. So kind of the idea, so the idea is that if I see that the channel is busy, then I'm going to defer access. And how long will I defer access? I will keep listening to the channel until the channel becomes free, so which is at this point. And then I'm going to wait for another period of DIFS before I can begin to transmit. Okay. There is a additional stuff which is done is the following, that in addition to that, I may also, to avoid the possibility that I may collide with the source again. So oftentimes what may happen is the source may, after sending this packet, may want to send another packet. So what I'll also do is, these other parties, they will also delay themselves by some random amount. So that's called back off. so the actual data transmission, there is a gap out here, which is at least DIFS, but DIFS plus certain probabilistic amount. And the reason that this is a very carefully designed protocol, that sometimes under some conditions, the receiver of the packet that source said may send an acknowledgement. So that's the ACK packet. And what happens is that there is another timing constraint that if you are going to ACK a packet, you have to do it within a time interval. So after you receive a packet, you are going to ACK it. And that turnaround time is something called SIFS, which is short interframe spacing. So kind of the idea is, party sends a packet. If you have an ACK, you have to respond quickly. Whereas if you are waiting to transmit any other packet on the channel, if you're someone else, then you have to wait for DIFS plus potentially some additional random amount of time. So this way, what is effect is happening is ACK is getting a priority because everyone else has to wait for a longer period of time after transmission of data ends, whereas ACK only has to wait, cannot wait for any more than SIFS. So with this and a whole bunch of other mechanisms, there's a kind of a complicated set of rules defining what happens in a channel like this. You basically create prioritization and collision avoidance, right? I mean, so this DIFS, where listen before transmit, is an attempt to avoid collision. These carefully orchestrated interval spacing amount of times let you create priorities. So when the data transmission ends, ACK can transmit more, has to transmit more quickly. So it will go ahead and grab the channel, whereas everyone else is now waiting for the channel to remain idle for a certain amount of time. So it's going to wait for a DIFS period of time and then some additional time before transmitting. Now, all of this sounds great. There is one additional snag which usually occurs, and that is the following: that we are operating in a distributed setting. So oftentimes this is something like this may happen. There's a node A, it wishes to send a packet to node R. There is a node B, which, let's say, it also wishes to send packet to node R, okay? Now, let's imagine that the range of radio A is such that it can reach R, but not B. And likewise, let's imagine range of B is such that it can reach R, but cannot reach A. Then what may happen is when A listens to whether the channel is free, and let's say at that time B is sending a packet to R, R is getting the packet, but A doesn't get it. So A thinks channel is free, and A will transmit the packet, and now at B, we will have a collision. So spatial separation, something which is called as hidden transmitter effects, okay, is a challenge out here, right? Because just because I am waiting to see that the channel is free doesn't actually mean that the channel is free. There could be a transmitter which is too far away for me to listen, but is still close to my intended receiver and is actually actively engaged in this. You may have another possibility out here that it's not, B is not sending to R, but maybe there is an R prime and B is sending to R prime. But since wireless transmissions are broadcast, so any transmission of B is not only going to R prime, is also going to R. So there is still collision which can happen. So this kind of scheme is not perfect because you may still, besides noise in the channel, you may still have collisions happening which the scheme cannot detect. So it is not collision prevention, but it's collision avoidance. You try to avoid, but if the network is very heavily loaded, you may still have collision and things may sort of not make it through. So this combination of spacing, so I talked about short interframe spacing, which is how we give acknowledgements the highest priority. This DCF, interframe spacing, or DIFS, this is how we check that the channel is free. And there is another one which is called PCF. It's an intermediate priority level, and the idea is this is how we give priority to those nodes which need to send on a regular basis. Okay, so any node to whom I have given the channel access to a microphone can say maybe get to transmit every 50 millisecond. Then every 50 millisecond it will transmit, but it will only wait for PIFS as opposed to DIFS. And this way it will get a higher priority access to the channel. So anyway, that's 802.11. So there's a whole bunch of stuff that goes on out here. One thing I wanted to bring out also is that nodes can go to sleep. So in particular, nodes which have been given periodic access via this PIFS mechanism, they can go to sleep and wake up on a periodic basis. Now, one thing which comes out is the following, that even if your MAC protocol is smart, but if you are not careful, there can still be a lot of implications. So one challenge is that messages to send, if you are just idly listening, radios consume a lot of power just while idly listening. And a lot of early protocols, including Wi-Fi, were designed in kind of a modality where radios just stay. Unfortunately, what it meant, upper layers were smart, okay? Even if upper layers were smart, by the time you hit the application level, there wasn't any differences. What this shows is the following: if you use a MAC protocol where, for example, you are not smart about preventing idle listening, and when it comes to sending information over a network, whether you do a dumb flooding or you do some sort of a smart protocol, they all consume the same power because your radios are up all the time. So in order to be efficient at the higher layers, it's also important that your lower layers are important. If radio has nothing to do, then your protocol should be designed so that they don't have to stay up just listening. So a lot of the protocols obviously kind of end up doing that. I would say around a dozen years ago or so, there's a whole lot of work on like rethinking MAC protocols so that we optimize them for power. At this stage, like industrial practice, so nothing terribly important from that perspective there. So one thing which makes kind of things in wireless side a little bit different is that unlike your wired networks, where networks are organized hierarchically, so what your device needs to know is how to, in order to reach a faraway node, what is the next node it needs to go to. So in your internet, you have IP addresses, and essentially these IP addresses are geographically clustered. So like your local area network, all the nodes will share a prefix. So for example, our ECE department at UCLA, its IP addresses are like 128.97. I think 93 or something. Okay, there are a bunch of such prefixes. But the idea is that if I need to reach a faraway node, I don't need to maintain a separate entry for it. I just need to maintain how to reach the network, and then I can send the packet to that network, and then within the network they can decide how to send to a specific node. That unfortunately doesn't work in case of mesh networks and all, because the mesh topology has no structure. So unfortunately, routing problem is a lot harder, and things can get sort of quite slow. You have to discover this topology. So a lot of so besides kind of the problem of power and power optimizing the MAC, even the routing problem becomes a little bit messier. You have to discover the topology. Every node will have to probably maintain a routing table. So if in a network like this, if let's say node A needs to send to node B, you really have two options, given that there is no structure to this. So all these nodes have some addresses, but unlike the internet where addresses are clustered geographically, all UCLA nodes share whatever, all nodes in a LAN share a prefix, for example. That's not the case out here. So you really have two options. One, at the time A has to send the packet B, I can try to figure out how to do it. So one way is A can flood the packet, right? And goes all over the network, and then B will also get it. The problem is that's incredibly inefficient. Another option is that I could try to make some guesses, like for example, what was the path I had last seen for B. So I can flood the packet, but as I flood the packet, I remember what path I took. B gets the packet, and then when B gets the packet, it sends back the path information to A. So now A knows how to reach B. And as long as the network topology doesn't change, that can work. Another alternative is that we do a initial discovery phase where every node learns how to reach every other node. So in a network like this, you have to somehow take care of this routing problem, and it's called as ad hoc routing. Because it's ad hoc because the network has no structure, and if you want to be efficient, at some level, nodes have to maintain. If my network has n nodes, I have to maintain a table with n entries telling me how to get to each one of the nodes. So there's a huge scalability problem as a result. Now, fortunately, unlike the internet, where you billions of nodes to worry about, typical embedded system type network, maybe you will have a few hundred nodes. So not as horrendous a problem, but still a significant amount of time. Or unfortunately, what happens is that these links may change because things can move. Like I may have a device which I move from one room to another, or in many cases, this could be like a vehicular network or something where things are moving more rapidly. So routing becomes a messy problem out here, and it's a second area where things are standardized. So NAC with this focus on power, and routing with its focus on all these changing topologies and all. So stepping back then, Wi-Fi, normally in Wi-Fi, we are used to the idea of access points, but Wi-Fi also supports kind of ad hoc mode. So there is a lot of, you can operate Wi-Fi in a way where you have a mesh network kind of thing. It's done less rarely, but it's certainly doable. So Wi-Fi, to summarize then, is obviously probably the most widely used wireless technology besides cellular, but it's high power consumption, and the fact that you really can't, there are a variety of reasons for high power consumption, but there are two main, one as I mentioned, modulation scheme. But there's another challenge that Wi-Fi faces is that when you shut down a Wi-Fi radio, and when you wake up, it takes a significant amount of time to resync, right? Tens of milliseconds. So it's not very good at rapid duty cycling. So Wi-Fi usable, but probably more for where your device is plugged in and have long-lived connections. Yeah. So what two other technologies have emerged, which roughly operate in the same space as what Wi-Fi and cellular are intended for, but have significant power advantages. And unlike BLE, which is really meant for very short range, these things are meant for larger spaces like a whole building or a campus or even city scale stuff. So what I'm going to do at this point is, before going into this, so 15.4 is often also called as ZigBee. Let's take a 5-minute break. So it's 7:05 right now. So we are going to resume at 7:10, and I'm going to go through ZigBee and then another technology called LPWAN or LoRa. So those are the two IoT specific things that have emerged and are present in a lot of systems. Okay, so 5-minute break, and then we resume. Okay, so let's resume. So, so we saw kind of the first half of the lecture, a little bit about Wi-Fi, and really kind of two main points. One is that in traditional wireless, the lower layers are not terribly uh, energy efficient, and part of it is that they were designed to keep the radio up all the time, as is the case with Wi-Fi. And the other aspect, which I didn't go into, but the radios use modulation schemes and all, which kind of make just generally kind of the whole structure makes it hard for rapidly duty cycling the radio. Then the other thing is that really they're not designed in a setting primarily where you don't have access to a base station, some sort of an access point. They mostly are optimized like both cellular and Wi-Fi, so that your device directly can talk to some network infrastructure. So while they do have modes where that is not required, that's not supported as a primary means. So that led to Wi-Fi standards, which are really designed to address some of these issues. So there are several things out there. Some are official standards and some are not so. So one which is an official standard, as you can see, is IEEE 802.15.4. And on top of it, there are built certain profiles and all, and they often go under the name of Zigbee. And this is probably the most commonly used thing when it comes to mesh type networking in IoT space. There is one competing technology, which is called Z-Wave, which is a privately owned a private standard, but and is dominant in certain product categories. But Zigbee is what is kind of the more standard one, and you will find it in smart lighting and all. So it's a little bit like Wi-Fi, except it goes through the same standardization process and all. But the main thing is really it uses a different physical layer, and it uses a MAC layer, which is also different. And IEEE standardizes these, and then some industry groups have standardized a layer above it, which deals with routing and such stuff. And collectively, and also as part of Zigbee, they have also defined different profiles, like, for example, for smart meter and smart lighting and things like that. So I'm going to describe a little bit for this one. And the reason is that these are designed specifically to address, excuse me, for hardware that is more duty cycle friendly, MAC protocols, which are more which optimize for power. And then finally, in case of Zigbee, there are routing protocols which let you do mesh routing and all. And this is something which is now supported in a lot of your products. Your Google Home Assistant, Amazon Echo, all these devices support Zigbee. So you can buy Zigbee devices and connect to them. So Zigbee, so Zigbee and these two kind of go hand in hand. And another term which is used for them is called PANs, Personal Area Networks, or WPAN, Wireless Personal Area Networks. So Zigbee is the higher layer protocol, and 802.15.4 is the physical and MAC layer. These are designed for lower data rates, but extremely long battery life. So like a few years type battery lives, but data rates of, let's say, small number of megabit per second or hundreds of kilobit per second. Through mesh networks, they can transmit over longer distances. So campus scale, or in fact, Zigbee is also used by power companies and all to read meter data. So smart meters transmit using Zigbee, and then through multi-hopping, they kind of take it to a central place in a neighborhood, and they're using cellular technology, they can extricate it. So it's being used, these application domains that I show out here, meters, sensors, medical devices, so on and so forth. Key thing is that it is designed for very low wake up time. So original Bluetooth, classical Bluetooth, okay, which is what this thing would compete with at short ranges, it would take many, many seconds to synchronize. Whereas Zigbee, the radio can wake up and be up and running very, very rapidly. So, so example of this, many companies make radios. TI, Texas Instruments is one. For example, they operate in what is called as a 2.4 gigahertz ISM band, and we saw Wi-Fi also does it there, Bluetooth also does it there. So ISM band stands for instrumentation, scientific, and medical band, I think, something like that. And kind of the idea is that this is a part of the spectrum, along with a few other similar ones, where when you operate a radio device, then the end user doesn't need to take a license, only to do it. So as long as the manufacturer certifies that their device is compliant with whatever FCC has required, then as an end user, you don't have to do anything. Whereas in every other band, you have to license the frequency. So like if you're a TV station wanting to transmit, then you have to go and buy that part of the spectrum. But here, you just need to buy the device and run it. So so it's kind of a free-for-all kind of a band to some extent. Yeah. So 16 radio channels, they are numbered, there's given some number, but the point is that they operate in this band from 2405 to 24, I think there's like 70, let's see, 24, yeah, so 83 megahertz worth of band. So it's a reasonable part of the spectrum, and there's a bunch of channels sitting there. So what they have are two types of devices, what they call as full function devices and reduced function devices. And kind of the idea is your full function devices are those which are powered up most of the time, or at least have a huge battery. So these might be things like smart meters or lamps or things like that. Whereas reduced function devices are those which are intended to be extremely resource constrained. So they implement only a subset of the protocol, and they are kind of like the leaf nodes. And these are usually things like battery powered sensors, or and actually some of the products are like battery powered electrical switches. They are not connected to electrical wiring, but they're just like little remote controls. These guys, the full function devices, they can be coordinators, as in they can play kind of a more important role in the network, whereas these reduced function devices, they cannot become coordinators. So a coordinator is a special node in the mesh network, in a Zigbee mesh network, which can provide, which can kind of like act as a little local hub for other devices. Okay, so essentially it's kind of like playing a role of a access network. And then PAN coordinator is one which is kind of the controller for the whole network. So essentially, what happens is that the whole network has this PAN coordinator, which is kind of dictates how the timing and other such thing in the whole network. There are other devices which can become a PAN coordinator. So the idea is that the main PAN coordinator for some reason disappears, like is powered off, for example, then someone else will take over. And then there are devices which cannot be PAN coordinator. They are kind of these tiny little battery operated devices. They can go to sleep, things like that. So the so your network can operate in a star topology, or it can operate in kind of peer-to-peer topology. And kind of the idea is that, let's see, most generally it looks like this, that the backbone of your network is made up using these full function devices, and then your reduced function devices talk to the nearest full function device. So essentially, multi-hopping takes place via a path which consists of these full function devices. And these devices are always up, or hopefully always up, whereas reduced function devices can duty cycle. So that's kind of the basic structure from a routing topology perspective. Then layered on top of it, with the help of, and one of these nodes, let's say this node would act as the coordinator for the whole personal area network. Okay, so now the way communication takes place out here is rather different from the way it happened in Wi-Fi. So remember, in Wi-Fi, we were letting things compete and all. Here, since power is important, so what they do is they impose a global timing structure out here. So the time in the whole network is divided into frames. So what we show in this slide is kind of this whole thing is a repeating time frame. So essentially the whole network operates in chunks of this super frame, and every super frame, this whole network goes through this kind of a schedule, and I'll describe that, and then it repeats again and again. At the very beginning of a super frame, there is a network beacon which is being sent. It's a special packet which has information about the network. So if your new device wakes up, it will just wait on a particular channel. There is a Zigbee network there. If there is a 15.4 network there. So it contains information about the network. It also contains information about what else is in that frame. So as you see in this frame, there are kind of a few distinct regions. So it has information about its timing behavior and all. Second, light blue colored area, which is kind of reserved for additional information about the beacon. But most importantly for us are these two regions, this kind of brownish color one and this greenish color one. Greenish color one is called the contention period. And within this, it operates like Wi-Fi. So nodes can compete, okay? And with that comes packet collision and stuff like that. And then the green area, nodes are given some slots reserved for them. So it's called guaranteed service. So essentially we can give a particular node that you always have access to whatever ith slot in the super frame. And that way it gets a guaranteed amount of frequency. So this is guaranteed, and this one is contention based. So if your device needs only once in a while type access and all, maybe contention is fine. Or on the other hand, it's like a sensor sending periodic data and all, then it would go for the guaranteed service. So with this structure, what it also allows to do is devices can go to sleep. So for example, if I am a sensor which will only transmit at a certain point in time, then as long as I'm in sync with the beacon, then I can basically go to sleep. So I'll wake up, listen to the beacon, and then go back to sleep, and then wake up when it's time for my time slot. So power reduction basically becomes kind of a dominant consideration out here. So unlike Wi-Fi, where primarily it was contention based, and then we had this weird priority mechanism to give kind of fake priority access, here the underlying mechanism is this strict timing, and then we set aside some area to do contention based stuff, but most of the other stuff is the other part is reserved for guaranteed services. They also have some additional features to provide battery life extension. It's also called BLE, but has nothing to do with the Bluetooth LE. So there are additional features in there which allows devices to sleep for a longer period of time. I'm kind of going to skip that. Now, it sits in the same band as the 2.4 gigahertz Wi-Fi. So one of the challenges that does exist is that if you have a Wi-Fi network existing in the same place, 2.4 gigahertz, kind of the older Wi-Fi existing in the same place as Zigbee, then there has to be some smart division of work within them. So Zigbee has features built in which detects Wi-Fi network and then kind of switches to other channels. But also what has begun to happen is that Wi-Fi, a lot of the newer Wi-Fi products are in 5 gigahertz band. So this is perhaps going to be less of an issue. So what we have seen thus far then is Bluetooth, Zigbee, and Wi-Fi, and they are complementary in some regards. So Bluetooth is kind of like megabits type speed, small number of megabits. Zigbee is even lower, kind of maybe Zigbee is faster than BLE, but slower than the regular Bluetooth. Wi-Fi is high rate. Newer Wi-Fis can go up to a few gigabit per second. In terms of range, Bluetooth is really meant for shorter ranges, tens of meters at best. Zigbee, because of its mesh, can go really high. Thing you can kind of, and Wi-Fi is again high, but it's high in the sense that the single hop is high, and could be hundreds of 100, 200 meter easily. Power consumption, depending upon things. So Bluetooth, classic Bluetooth would be moderate, but BLE can be super low. Zigbee is also quite low, and Wi-Fi is high. So they occupy different territories. But one thing which we still miss in this thing is that none of them are for city scale. When it comes to city scale, at least in this picture, your real option only is cellular. And this is the one place where some additional action has begun to happen. So which I'm going to talk about next. Less kind of a more high level description. So again, this is room. This is again campus, let's say campus or organization, and this is also campus. But they achieve their goals rather differently. Okay, this is mesh, and this is access point plus wired backbone. Before I go to city scale, one thing which also has begun to happen is, I'm sure you have seen these products for Wi-Fi, which call it mesh Wi-Fi. So and the way they work is the following. So as you know, normally you buy a Wi-Fi access point or a Wi-Fi router. What these mesh Wi-Fi products do is you buy multiple Wi-Fi access points, okay? And then these multiple Wi-Fi access points create a mesh between them. And then your laptop like talks to the nearest access point. It's a little bit like what we saw for Zigbee, where the access points are my coordinator nodes, and then full functionality nodes, and then my leaf nodes are the reduced functionality nodes. So except that the power consumptions are just totally different. I mean, these mesh access points are like big, they need to be plugged in, those kind of devices. Many of the products you see now like can act as such. So like Google's Google Home Assistant, for example, can serve as access point in a mesh network. Apple used to make something called Airport, which they stopped making a couple of years ago, were like that also. So there's a lot of sort of confluence between these, but still Zigbee, in terms of power consumption, is much lower power than what Wi-Fi is. So they're catering to different speed and power points, despite this mesh Wi-Fi kind of emerging. So mesh Wi-Fi's role is to handle the following problem, that many people live in homes where they do not have an Ethernet backbone. So, and yet at the same time, a single Wi-Fi router cannot cover the whole home. So this is providing solution to a coverage problem, that you can have Wi-Fi access points in different parts of your home and yet not have to deploy Ethernet. And usually what these products do is they use two frequency bands. They will use one frequency band and a separate Wi-Fi radio to talk between the access points, and then a different frequency band out here. So they'll often have like dual radios or even more. There are a variety of ways to kind of create this thing, but there are many products. Google makes one, Amazon has something called Eero. So they're all kind of doing this. You can also use these in a at a campus scale also, right? I mean, so instead of wiring access points, you can use the mesh Wi-Fi. But all of that does come at a cost, because if you're using wireless only, then the bandwidths are lower than if you have an Ethernet backbone. Okay, so let's move to city scale. So none of these technologies solve the following problem. What if we want to do urban scale sensing? I'm a city of Los Angeles. I want to see what's happening to the city infrastructure all over. What technology should I use? And pretty much, and yet I want these sensors to be lasting for long times. They may be battery operated. Maybe I'm trying to detect whatever traffic or fires or things like that. So one thing we can certainly do is we can use cellular, and indeed LTE and 5G are targeting that space. And I mentioned earlier last time that 5G is advertising like sub-millisecond latencies and all. But this is a space where there are a bunch of other players which have also emerged. And this whole thing is called LPWAN, low power wireless area networking, or LPWAN. So there are a bunch of Sigfox is a big company, LoRa is a kind of a sort of a standard, NB-IoT, and a bunch of these others. But there is also heavy competition from 5G, IoT, and LTE. So I want to describe how one of these works, and that one I picked is LoRa, just to give you a sense of what happens. So LPWAN use cases are things like tagging devices, city assets, things like that. You have low data rates, but you want stuff to last for years. Okay, that's the kind of stuff. And you are willing to deploy some gateways, but not at a very high density. So like you want coverage where a device can talk to the gateway, which might be a few miles away. Okay, so a few gateways, perhaps located on rooftops and all, should suffice. Okay, or if you are a UCLA, maybe you want to keep track of like every cargo truck, every movable asset. Okay, maybe you want to tag them and all. So LPWAN is really for that application. LPWAN tags, LPWAN sensors, these kind of things. There are several cities now which have LPWAN deployments. Pittsburgh probably is the most densely instrumented one in this regard, mostly because of work out of CMU there. They have some large scale activities happening. So LoRa operates again in the ISM band, except they operate in a sub-gigahertz ISM band. So I mentioned the 2.4 gigahertz ISM band, but there is also an ISM band which exists between 900 to 915. And I think there is another ISM band which is somewhere around 400 megahertz. Okay, and for city scale stuff, it is good to have lower frequencies. Why is lower frequency good for city scale stuff? Anyone? What might be the reason that we would prefer, instead of 2.4 gigahertz, we are preferring a lower frequency?
Lower frequency will attenuate less, so more area will be covered.
Yeah. So and it will penetrate through walls and all. What's the penalty?
Antenna size?
Yeah, antenna size, as you can see out here, right? Big antennas, because it goes with the wavelengths, absolutely. So, but LoRa, which is, again, most of these standards are really from specific companies which kind of have caught on. So it's really designed for thousands of devices per gateway, very low data rates, kilobit per second, but long lifetime, okay? And at distances of like miles, okay? So very different space. And the other thing is, because it's operating in the ISM band, unlike LTE type stuff where you have to pay money, this is all free. You buy the devices, you deploy it, and there is no recurring cost that you have to pay. There's no like cellular service that you need to subscribe to. So there is a lot of stuff out there. These guys use SPET spectrum modulation. So SPET spectrum, I mentioned earlier on that one way we can separate out things is via code. So in SPET spectrum, what happens is every time I need to send a symbol, or let's say a bit, so like, let's say I have to send 1 versus 0. Normally, we will just send 1 versus 0. But here in SPET spectrum, when I have to send a 1, I'm going to send a sequence of faster bits. They're called chirps. So kind of imagine some sort of a waveform consisting of more rapid bits, okay? And 0 will correspond to the a similar sequence. And kind of the idea is that the code that I use to send 1 or 0 kind of defines the code for my network, and multiple coexisting network can use different codes, and how long my code is describes how what is the ratio between my symbol rate versus my data rate that I am sending out. So that is called chirp spread, which is that rate between, like, to send one, I'm actually sending a sequence of n chirps. So n basically is the spreading factor. I'm spreading one bit over n chirps, and longer my sequence is, slower my data rate is going to be, but less chance that a collision with another network with a different code that would happen. So spreading factor affects the data rate, symbol timing, as well as your ability to detect it. Okay, so if you use large rates, as in large spreading factors, then you can send things over longer ranges. The MAC layer part and all is kind of a little bit like Wi-Fi or simple Aloha. That is, you send and conflict happens and then you recover from it. The topology is star topology, so there's no mesh routing in this thing. So you have base stations on top of buildings typically, or street poles or things like that, and they may themselves use something else for connectivity back to the cloud. Maybe they are using 5G, maybe they are Ethernet wired up, but the MAC protocol out here is super simple. Okay, Aloha. So now what happens out here is the following. When a device transmits in LoRa, its transmission may be heard by multiple base stations. So what happens is these guys do what is called as MAC in the cloud. Essentially, the base stations are super dumb. All they do is they send things back to a LPWAN server, which is over kind of the internet. And this LPWAN server in a given time window may say, hey, two different base stations saw the same thing, and then it can combine those packets to do a more reliable recovery, and then it can send back an ACK. The reason, because of all of this, what's happening is that the turnaround time, right? The packet hits the base station, goes to the cloud, and then goes back. So the packet to ACK delay is quite large. And that is why, in part, why the data rates are so slow. Also, besides the fact that we are optimizing for power as well. So gateways forward everything to the server, and all the intelligent stuff is happening out in the cloud out here. So MAC in the cloud in this particular case. So what all of this does is, so very high spreading factor, so that it's a very robust thing, very low data rates, and all. What it gives us is really long range. So you basically have a free network which can operate really long range. So this is from Pittsburgh area. So what you see out here is kind of the radio signal strength that they have received, and you could see that the received threshold is around out here. So it pretty much means that they can go to, I mean, many kilometers of range quite successfully. So like in an LA context, I mean, if you have something like this running on UCLA, you can easily just single hop go to whatever, Santa Monica, Oceanside, stuff like that. Probably not to the hills, but long range. So for city scale stuff, this is great. So if you are a power utility, or if you are cities transportation, or you just want to keep track of where the buses are or things like that, and you don't want to pay for one of those cellular services because then they charge by the bytes and all, this is a great technology, and also super long lives. It also, because it is using the sub-gigahertz bands, it also penetrates the buildings quite well, as kind of this map shows. And then finally, really, in devices like these, with the microcontrollers and all, your bottleneck really comes down to when you are transmitting. So a lot of effort goes in minimizing the transmit power. Roughly speaking, your operations versus memory versus transmission, right? Transmission reception. The ratio is, if this takes one time unit or one energy unit, this will take 10. This will take 10, and this will take 100. This is probably a reasonable, whether you are looking at time or whether you're looking at energy. This is a good rule of thumb that you can adopt. What it means basically is that you can spend lots and lots of operations to avoid sending something. In fact, sometimes this ratio is even more, like cost of one operation, cost of sending one bit, maybe like thousands of operations, okay? Excuse me. So that makes in these systems a lot of local processing. So like, for example, if you have a camera or something like that, you're not going to send the image over. You are going to send the decision made from that image over. So which is why oftentimes now you will see people talking about edge intelligence, right? Kind of the idea being that we do our entire inferencing, like from data to reaching an inference, we really do it on the edge, as opposed to, as many of you are doing in your course projects, for example, sending the data to the back end and running on MATLAB. That's not really viable when you are operating on these kind of kilobit per second type budgets, right? Okay, so just never going to happen. So a lot of work now basically is happening in kind of making sure that I can do things locally. The next whatever trend towards is going to be edge learning. So let me draw a distinction. Edge intelligence says I have a model, and given the sensor data, using that model, I can make an inference, like whatever, if some sensor data or camera, did I see a car or did I see a person? And that, I guess, at this stage, the technology is such that we can do very well and very power efficiently, provided I have a model which is sufficiently compact and is not changing. We know very well how to do compact models. As to whether a static model is good enough kind of depends. In many applications, it's no longer the case that you can learn a model and then never have to change it. You often have to change the model. And that we don't know how to do that very well, because learning a new model is still super expensive. So right now, I would say for LoRa kind of things and all the applications where it works very well is where your environment, where your needs are relatively static. You learn a model offline, you distribute it, and you don't have to change it frequently. Once in a while, you may have to change it, but that would be a conscious decision. It will not be great for applications where your models are changing quite frequently, because we don't have the bandwidth to send all the data to a central place to relearn a new model. And at the same time, we also don't have computing at the edge to learn a new model, neither computing nor memory. Okay, so there's a class of applications which are still out of bound for something like this. On the other hand, for example, on your phones, which are more power rich, you plug them at night, things like that, learning at the edge is certainly happening. In fact, a lot of applications where Apple, Google, and all do model learning and all quite frequently, making use of the data that your phone is seeing. So that we are not here yet with LoRa type stuff, but maybe in some distant future, we would have that as well. Okay, so to summarize this whole thing, there are many different technologies. I think I had shown this slide at the beginning of the BLE lecture also. So I've covered some of them. I mean, Zigbee and LoRa are kind of the two interesting beasts, and they're pretty cheap. You can buy little, just like you can buy USB things for Bluetooth, you can buy them for LoRa and Zigbee. LoRa antennas tend to be big because they are sub-gigahertz. Zigbee is 2.4 gigahertz, so they tend to be tiny. Z-Wave is the same space as Zigbee, and it's not open in the sense that you can't make your own radios and all, but the software wise it is open. And Bluetooth is the third big thing. I think these are, Ant at this point is largely dead. It used to compete with Bluetooth, but I think at this point there is really no need. Wi-Fi, there have been lots of attempts, many startups and all who have wanted to make low power Wi-Fi, but never really honestly panned out. I think its niche really, or whatever, its use case is going to be basically hundreds of megabit to gigabit per second type applications. And then 4G or 5G, and I guess in a few years, 6G. It is making a play for IoT and embedded space. But the problem, I think, at the end of the day is always going to be the business model, the payment model. Here, any services that you do, you got to subscribe for it, because eventually they have to be monetized. So it's the distinction between this and this may very well boil down to the money part of the equation. Okay, and I think they're all kind of overlapping at some level. And of course, the data rates tend to be a lot higher here, right? I mean, and accordingly, power consumption. I'm sure you have read that 5G radios are a pain in terms of power consumption. So kind of still performance points are different. I think another one which is emerging, which is really going to be something to watch out for, is satellites, right? For the longest while, satellites were reserved for very high cost. You are in the middle of Himalayas, that kind of applications and all, or you are a US military and then you need it. But I think with the new stuff which SpaceX and a couple of other companies are deploying, we are headed where for a lot of IoT applications that might actually be something of an option. If you are a group installing sensors out in the forest and all, maybe your gateway can have that and it would be at an affordable price point. So new stuff happening, but I think pretty much in the other tiers things are headed. Bluetooth will probably at some point have higher rate, even higher rate versions, maybe ultra wideband and all. So there will always be that, but roughly speaking, you have this really small space onto larger ranges. Another one which finally is I didn't talk about is body area. So this is a class of application where you have variables talking to other variables, okay? And as we begin to get into more and more medical type devices, things will happen there. Right now, they primarily make use of Bluetooth or Zigbee in some cases, but unclear what would happen. And then body area also includes implantables, so things which are being put inside the body, brain implants and such. So the jury is out there as to whether what kind of technologies will emerge for that application. Okay, so I guess the only closing message I would leave is that when you think about these options for your application, there's a whole bunch of different dimensions you have to consider, right? I mean, what rate you want, what range, what power consumption, stuff like that. And of course, as I mentioned, in some cases, it's a subscription cost, which matters. In some cases, the hardware cost. There's a bunch of these things. Ability to deploy an infrastructure, whether your application is latency sensitive, if you're trying to close a control loop. So given how some of these things have different characteristics, and you can attempt to plot the others that I talked about. In this case, satellite, for example, tends to be higher latency. You have to kind of go all the way up. So they all kind of rely on different parts. And so no one solution. One really has to think about these. Other interesting thing is that there are lots of companies that have emerged which basically operate these infrastructures, particularly for wide area settings. So essentially, they take care of all the pain. You just buy the device and subscribe to them. Okay, so they are kind of in the same space as what cellular companies do for the phones. And some of them indeed just bulk buy from the cellular companies. So like, for example, T-Mobile has T-Internet things. AT&T has something similar. Amazon has this very cool thing called Amazon Sidewalk. Anyone heard of it? Amazon Sidewalk? They've been in news lately. If you have, so what Amazon Sidewalk is doing is they are turning your IoT devices into access points. So essentially, if you have a Ring doorbell or if you have an Amazon Echo device, Amazon has pushed a firmware update in recent few weeks. And what they're doing is they basically, if your neighbor happens to go past your home and then your Ring doorbell, your neighbor's device can connect to your Ring doorbell and then connect back to the cloud. So essentially what they're saying is that by stitching together the devices that Amazon now has all over, they can create their own network infrastructure, because it's a lot of people are buying these Echoes and Rings, whereas expecting that people will make their home gateways to be Amazon is unrealistic at this point. So Amazon is kind of doing this side entry into creating what arguably would be one of the largest, very low rate urban scale network. So this could actually be an interesting competition to LoRaWAN kind of things. Essentially, by having access points everywhere, basically for free, they can achieve this thing. And there's a technical paper that they have where I think they say that the data rates that they queue up, remember their model is they are essentially stealing bandwidth from the existing Amazon devices. They're saying it is only around 40 kilobit per second, point being that it's very low. So Sidewalk can actually be a pretty interesting game out there. Of course, how people receive it, there are all these issues, my data going through my neighbor's devices, my neighbor using my bandwidth, all those kind of issues need to be worked out. But that's an interesting play. And then there are a whole bunch of these other companies which offer kind of services at different stack. So I'm going to stop with this. We are going to pick up on Monday. So Monday would be a guest lecture. I will be there, of course, but it's going to be by a student of mine who's going to talk about a topic called reinforcement learning. But it's basically a new way, a more machine learning driven way of doing control. So we have talked a lot about sensing in the course, but we never really talked about how we close the loop. So I wanted to expose you guys to that topic a little bit as well. So my student Sandeep Singh Sanda, he's going to give a lecture on Monday. Okay, so I'm going to stop at this point. And if you have any questions, just shoot on Piazza. Otherwise, I'm going to rush today, so I'm not going to stick around for questions. I have some deadline to take care of, so sorry about that. But if you have any questions, just shoot me an email. And those of you who have not submitted your homework, remember the late deadline is 4 days from Tuesday, so midnight. So I think just make sure to submit. And if you are a few minutes late and all, I will not penalize. I know some of you emailing me about that. You'll run into last minute snaffles, so I tend to ignore those. Okay, see you on Monday.